title of the lecture is called Introduction to Toric Topology. The toric topology is not a very popular word, so many of you might not know what that is, but some of you might know what toric geometry is. So toric geometry is a field, a certain field of algebraic geometry. And toric topology is topological. It has a lot of influence by toric geometry, and we try to translate into topological terms. And also it is related with, a lot related with combinatorics and symplectic topology. But today I'm going to talk more about the aspect of topology and related with the combinatorics. Okay? But all these are motivated and a lot of influenced by symplectic geometry and also toric geometry. So when we say, let me just start up from the definition. Many of you might know, but still we have many new graduate students. So the group action, so when we say G is a Lie group, and M is a manifold, then we say G is acting, well, some people just, I don't know. When I studied group actions, nobody used this notation, but these days, many people are using this notation, so I will just follow. G is acting on manifold. So I'm not going to write it down, the definitions, but this means almost similar, that every element in G is you may consider this is a diffeomorphism, or if this is a topological manifold, then this is a topological homeomorphism, but you may consider this is a diffeomorphism. So it's a collection of diffeomorphism, and the multiplication is just a composition of two maps, self-map into itself. So that's a group action. So in this case, G acts on M, or M is a G manifold. We say this is a G manifold. Okay, let me give you one example. Very simple one. So G is a circle group, which is set of all zeta and then M is complex plane, and then group element e to the I zeta is acting on an element. This is just multiplication. Let's see. Group action, or I will say this way. So that's the multiplication. And then when you have a G manifold, then you can also think about its orbit space. So orbit space, it's on here. You have a projection. But this orbit space is nothing but identification space with an equivalency relation where X is equivalent to X. So if X, you have X, and it is translated by another element in the group, then they are equivalent. So in this case, this is called the orbit space. And this map is called the orbit map. Okay, so what is the orbit space of this one? In this case, so here you have complex plane, and any plane, any point, and then by the element of a group circle action, it goes around the circle, right? So its orbit, this is M, and its orbit space is M quotient G, or S1. It's nothing but left half line. Okay, so it is half line. This is very simple example, but this is also very important example for toric theory. One of the basic examples. So let me give you more slightly n-dimensional version of this. So let's say G is Tn, which is S1, S1. Okay, so this is called the N torus. So this is a group, Lie group, and then M is C to the nth, and then group action here, e to the I zeta 1, e to the I zeta n, is acting on Z1 up to Zn, but this is an element in C, and this is an element in S, T to the n. And this is e to the I zeta 1 coordinate-wise multiplication. We're taking coordinate-wise multiplication. Then each coordinate, if you take an orbit space, then each component is just a half line. Okay? And you have half line, n half lines. So it becomes G, which is m quotient s t to the nth power, which is nothing but here, this is Cn, so the complex n dimension. As a real manifold, this is same as R2n, right? When I say this is a manifold, this is a real manifold, not complex manifold. This is real manifold. So this has, you view this as a real space. Then its orbit space is same as R. Its power. So when n is, for example, when n is 2, what happens is this orbit space is nothing but here. 오늘 날씨가 흐려서 자꾸 부러지네요. This is the orbit space. Okay? And look at this point. Here. Inverse image. So here this is in orbit space. So what is this inverse image of this point? The origin of this point. So this point corresponds to the point fixed by T2. So this means another notation here. When you have a G action, then M of some G is set of all points in M such that Gx is x, which does not move at all by every element of. So this can be also defined for any subgroup. So H is a subgroup of G. Then you can also define same thing. So this is a fixed point set by subgroup H. So usually, which is bigger? The point which is fixed by more homomorphism, more maps should be smaller, right? So this is included in here. Okay. So this is opposite way. So this is fixed. This corresponds to the point which is fixed by the total space, total whole group. Where is it this correspond to? The line which corresponds to this line. Here, this is the point where fixed by what? So this part moves here, but the second part is 0, right? So whatever you have any element here, this is 0 part, so it is fixed. So this is fixed by subgroup, fixed by what? 1 times S1. And this is this pi inverse. So this part is fixed by MS1 cross 1. Right? So this part is nothing but, in this case, C. Okay, if this is C, C times 0. No. 0 times C, and this corresponds to C times 0, right? Okay. So if you have a three-dimensional case, then picture is more like this. And then here you have vertex, which correspond to the fixed point set by the whole group, and each edge correspond to the subgroup fixed by rank 2 subgroup. Okay, and the face, you see you have three faces, right? So three faces correspond to the fixed point set by rank 1 circle subgroup. And then interior is the point with free action. So no fixed point at all. Okay? So this kind of action is called the standard action. Now, in toric topology, we would like to create a manifold which looks just like this locally. Okay, that's what we are trying to do, and we are trying to investigate what it is like, what kind of property does it have when some manifold has locally like this. Okay, so not in whole toric topology, but especially the area that I'm working on is this, so don't be confused. Okay, so as you can see, what does this one? This one looks more like there's a very familiar term in combinatorics called a polytope. And a polytope is a convex hull of endpoints in Euclidean space. But you can also consider polytope as the intersection of half spaces by the plane, and you cut it by the planes, hyperplanes, and then it's the interior, it's polytope. So polytope is like something like this. So half space, half space, half space, half space, and this part is polytope. Okay, but among polytopes we have something called a simple polytope of dimension n. That means at each vertex exactly n facets are intersecting. So what is facet? Facet means codimension one face. So if you have a polytope like this one, then at each vertex, 1, 2, 3, three facets, in other words, codimension 1. So two-dimensional faces intersecting. Here, two-dimensional face, three two-dimensional faces intersecting. This, you are also considering interior. So, and then something which this is simple, but something which is not simple is like a pyramid. Okay. So all other points, you have three facets intersecting, but here, four facets are intersecting. So this is not simple. Now, when you look at this orbit space, if this is dimension 2, then you have two facets are intersecting. When you have dimension 3, three facets are intersecting. So this locally looks like a vertex of a simple polytope. Right? This looks more like a, so this one is a neighborhood of a vertex of a simple polytope. Okay. So we want to construct a manifold which locally resembles this one. So let me just give you the definition here. So let Pn be a simple polytope. So n is the dimension of the polytope, okay? Mn, M2n dimensional. So this manifold is a 2n real dimensional manifold. Is a Tn manifold. So that means this is a smooth manifold with Tn. So half-dimensional torus is acting on it. And is called a quasi-toric manifold. This is called a quasi-toric manifold if and only if So I'm not going to give precise definition of this, but each locally this each chart you have some chart which looks like an open set of this Euclidean complex plane, open neighborhood of complex plane, open set of complex plane. That's called the locally standard. So Tn action is very restrictive action, not a very easy one, but not a very complicated one, but very simple, but very restrictive. And the second, there exists pi from M2n to Pn such that each orbit goes to a point. Okay, each orbit goes to a point. In other words, this is an orbit map. So each orbit goes to a point means this is an orbit map. But why do we need a polytope structure here? So polytope structure keeps all the record of this fixed point data. So what is that? Each k-dimensional orbit sends to a point in the interior of a k-dimensional face of Pn for each k. 0. So here, if you look at this, then you might see. So if you have a k-dimensional orbit, okay, at most it is the free part is n-dimensional orbit, okay, and then n-dimensional orbit goes into the interior of the polytope. And on the facet, interior of the facet, okay, relative interior of the facet, then it's orbit of dimension k minus 1, n minus 1. So in other words, it goes to the points which is fixed by a certain circle subgroup goes to the facet. Just like this. So this is called the quasi-toric manifold. Let me give you an example. So here, all those people who know what a toric variety is, all projective, smooth, toric variety are quasi-toric manifold in algebraic chart. But there are some quasi-toric manifolds which are not toric varieties. Okay, so I'm not going to tell you more about that. But let me give you a very simple one so that you can get better understanding about what this is. So here, definitely, Cn is a quasi-toric manifold. This definitely is an ideal case. But Cp let me just say CP2. CPN is also generally this, but CP2, complex projective space. What is this? This is the space of C3 divided by relations that Z is related to lambda Z, where lambda is in C minus 0, and G is in C. Okay. So here, each element can be represented as a 3-coordinate. And in order for this one to be a quasi-toric manifold, this should have a torus section. But this is real 4-dimensional. So you need T2, torus T2 action. Okay, how can we give a T2 action here? T2 action. So e to the I theta 1, e to the I theta 2, acting on Z0, Z1, Z2 is just like a just remove, except for the first coordinate, you just multiply component wisely. And then so this is a quasi-toric manifold. If you have this kind of action, why? Because polytope here is delta 2 triangle. So let me just simple convex polytope delta 2, 2-dimensional simplex. Okay, and here. So this is the vertex. This is the orbit space. So you may consider this as the orbit space of 2 action. And the inverse image of this one is what? How many fixed point sets by the whole group here? There are 3 fixed points. One is, so pi inverse, it goes to, if you have Z0, 0, 0, then you multiply any group element here, does not do anything, right? So it is fixed. Another one here is that if you have 0, Z1, Z, 0, then here you multiply group element here, then what happens? The second term is multiplied by a non-zero constant. So in projective space, they are same because of this relation. So it doesn't move. And this one goes to 0, 0, Z1. Okay. And then what is this one? This face, this is facet. So inverse image of this one, pi inverse, is the set of points okay. So this point, this one is fixed by a circle subgroup. What kind of circle subgroup is fixing? This one is fixed by S1 times 1. This and this face inverse image is nothing but so 0, Z1 and Z2, and this is fixed by what? Which is isomorphic. This is a diagonal circle action, so this is like isomorphic to circle, but only diagonal circle subgroup. So if you multiply the same e to this etc., it's a diagonal element here, and then you got same. You can pull out this and the same number, so it doesn't move. So each fixed point, each facet correspond to the submanifold fixed by a circle subgroups. So here the combinatorial structure in this polytope contains all the fixed point data of this section. So that's why topologically Pn is just a constructible space. It is topologically same as a point, so it is not interesting. But because of the combinatorial structure, it has all the action is encoded here. Now, okay, so suppose you have a so this is a quasi-toric manifold. Quasi-toric manifold. Okay. Then, so let's say F. Suppose you have m facets. Okay. In this case, how many facets does it have? 1, 2, 3. 3 facets. Okay. Suppose you have that. Then, for each facet, here, this inverse image corresponds to the manifold fixed by certain subgroup, circle subgroup of Tn. It corresponds to the certain circle subgroup. Okay, but the circle subgroup of Stn, circle subgroup, corresponds to a map. It corresponds to a primitive vector integer lattice. Primitive means it's what? It is not. What is primitive? So if this one is length 2, okay, 0 from 0, 0, 2, then it has 2 things, right? It's not primitive. So in other words, you have all these lattice points, and then this one, and in the middle there is no lattice point. Then that's the primitive one. Okay. So 0, 1, this is primitive. Okay, and 2 and 1, this is primitive, right? So there's a primitive vector. So this one, if this is a PQ, for example, in Z2. Then what does it correspond? You have a torus, and then rotation by t times in this direction and q times in this direction gives you a circle subgroup. So it corresponds to that circle subgroup. So this circle subgroup corresponds to the lattice point in here, but it should be primitive vector. Okay, so we just call it lambda of F1 in Zm. So for each facet, we will correspond to the subgroup, circle subgroup, fixing the inverse image. But this circle subgroup corresponds to a lattice point in Zn. So namely, we can define a map from lambda to set of all facets to a lattice point. But actually, it doesn't matter whether this is +1 or -1. So we can just, it only gives you a direction, circle subgroup. So it doesn't matter whether it's this direction or that direction. So it doesn't matter. You have this one, this map. Okay? And then it should satisfy one condition. It's called the non-linearity condition. In order for this action to be, effective, what happens is that at each vertex, this is vertex, and then you have F1, F2, let's say Fn. So this is a simple polytope. So at each vertex, we have exactly n facets are intersecting. So let's say at V, Fi1, Fi2. So let's say V is Fi1, Fin. N facets are intersecting. And then we have a primitive vectors lambda Fi1, lambda Fin. So in n-dimensional lattice, you have exactly n vectors. And we want them to generate basis, to be an integral basis. So condition lambda Fi1, lambda Fin, n-dimensional, form a basis for Zn. So from topology, we have sort of reduced to some combinatorial or algebra combinatorial conditions on the polytopes and there. So what we have done is this. It should satisfy this. So this exists such that satisfies star. So star is satisfied. This star. So what we have done is that, so set up all quasi-toric manifolds. Category of this. So you may associate, so for each m, p or pi, what you have associated is a polytope Pn. You may just Pn, and with this function, which maps to each facet to a primitive vector in Gn, satisfying this condition. So from manifold, we have this sort of invariant, combinatorial invariant. On the other hand, if you start with the polytope, simple polytope, and on each face, you define vectors, which satisfies this condition, then you can construct a quasi-toric manifold. So here this expression, this argument shows that if you have a quasi-toric manifold, then you can produce this characteristic map on polytope. But forget about everything. You just have polytope. And you have a combinatorial object like this characteristic vector function. Then there exists a manifold, uniquely manifold, which has Tn action, which is a quasi-toric manifold. So there is a way, I'm not going to explain it, but there is a way that you can associate this. So this topological object of quasi-toric manifold, studying of that is same as studying this polytope with satisfying simple polytopes, satisfying these combinatorial or algebraic conditions. Okay. So one of the questions which where combinatorists might be interested in is that given polytope, what kind of quasi-toric manifolds can there exist? Or is there, for a given polytope, does there always exist a quasi-toric manifold? In other words, can we find a map on its facet which satisfies these simple conditions? But the answer is not always. There are some polytopes which does not admit such kind of. Okay? But anyway, so now, since I'm a topologist, this is a relation. And I want to know more about this quasi-toric manifold, okay? So for a topologist, what is the most interesting invariant? Cohomology. Okay, so we want to calculate this cohomology of quasi-toric manifold. And there is a very nice formula for quasi-toric, arbitrary quasi-toric manifold. Okay, so okay. When people consider group actions on manifold or space, usually the first thing they think about is something called equivariant cohomology. So what is equivariant cohomology? So M is a, in general, M is a G space. Then people consider something called equivariant cohomology of this. And what is this? This is nothing but the usual cohomology of the space, something called EG. Okay, whatever it is. I'm going to explain it, but it's called this. Okay? Some topological space, which is, and then this one, what is the EG? Is a contractible space with free G action. It's called this. And then here, this orbit space is usually denoted by BG, and it's called the classifying space of G. So it is called the classifying space. And what is this? This one is nothing but EG, this space, times N, with the identification, which one says that E and M is equivalent to E of, don't worry about this one, but we usually have this right action and this left action, and to make an action, you put minus. But if you don't want it, then you can just write this way. Okay, left action, left action. But anyway. So you are modding out by this relation, then it becomes this. So this is a cohomology of the space with some action is involved. And this action here is related not only here, but also here. So this EG does not have anything to do with the manifold, but because we are modding out this way, it gives you some idea about, it is related with the group action. But unfortunately, for the quasi-toric manifold case, what is known is that, so M P is a quasi-toric manifold, then H star G of, so when I said star, I mean cohomology, I'm not just talking about cohomology group level. It's a cohomology ring. So it is a ring, as a ring. So as a ring, cohomology ring, so our group is torus. This is isomorphic to something called a phase ring. Or some people just want to say this one as a Stanley-Reisner ring. And I don't know why it is called the Stanley-Reisner. Some people last workshop in claimed that it should be Reisner-Stanley group, right? Alphabetical order. But Stanley seems to be most strong person, so it's not fair, right? It's not mathematical. But what is this? This one is, suppose this one is a P has M facets, F1, Fm, then Zp is isomorphic to Z, V1, Vm. Each Vi corresponds to the facet, the variable corresponding to facet, with an idea such that Vi1 times Vik is 0, where Fi1 intersection Fik is empty. So this is a very interesting relation, but this ring is a truncated polynomial ring, but this ideal is given by the multiplication. It's the monomials, by the monomials, but it's monomial here is that the corresponding element, if their facets does not intersect. For example, the facets are making loop, like a belt, then it contributes to the ideal. So this can be easily calculated, okay? But what does this say? This says, suppose we have a P, polytope. We have one quasi-toric manifold, and we have another quasi-toric manifold, and then a covariant cohomology of this one and this one. They are isomorphic because their base, orbit space are same. So this not tell you anything about the cohomology. The real, this not tell you anything about, not anything, but not much about the manifold itself. But it only tells you about phase ring of the base space. Okay, so what about this? Cohomology? Usual cohomology of this. Okay, usual cohomology, not a covariant cohomology, but usual cohomology. So this is usual cohomology with integer coefficient. This one is isomorphic to this ZP with some ideal J. Okay, so in other words, this is G, V1, Vm with, let me call it this ideal to be I. So some other ideal J. And what is this J? Here, I defined characteristic for quasi-toric manifold, you have this characteristic function. Okay, you have m n-dimensional vectors, integral vectors, okay? So just to write it down. So what is this? So lambda is a set of all f to z, m. And then, so lambda f1, lambda f2, lambda fm. So this is an m by m matrix, right? So lambda 1, 1, lambda n by m matrix. So what should n1? Is this usual notation? Lambda m 1n lambda m n n. So this is let me call it lambda. This is n by m matrix. Then this ideal J is generated by the linear equation defined by this one. So lambda 1 1 v1 lambda 1 m vm. This one linear equation, and then another linear equation, and also lambda n1 v1 so that's a cohomology ring of this one. Okay. So let's calculate this cohomology ring of some of the quasi-toric manifolds, which might be interesting, okay? Because you said this looks very awfully complicated, but it is not complicated. I'm going to tell you why. So there is some quasi-toric manifold called the Hirzebruch surface. This is an object where many people in algebraic geometry or topology, they consider this object. But here P, in this case, P is just square. Okay. And then here, let's say, this one is F1. Let me go to F2 and F3, F4. So let's define quasi-toric manifold F1. Lambda F1 is 1, 0. Lambda F2, or rather put it in a matrix form, simply, like this. So let's say lambda will be 1, 0, 0, 1, 1p, 0, 1. And you can check this linearity condition easily, because at this vertex, two facets are intersecting, so F1 and F2. So this one. And this matrix determinant is 1. So it generates a basis. And then F2 to 3, so this one. What is the determinant? Determinant is -1. So it is either +1 or -1, then it's equivalent to saying this is a basis. So you can check it. And then this one is a nice one. And then this is the Hirzebruch surface. Another way of understanding this one is this. This one is a projectivization of this So what is this? This one means this. You have a complex projective space P1, which is sphere S2. Okay, this is S2. And then you have a complex bundle, and this is a sum of line bundle, two line bundles, but one is a trivial bundle. And the other is a, complex bundle has a tautological line bundle. Okay, complex line bundle. You tensor P times of this, and then you add it. So this is a complex two-dimensional fiber. And you take a projective, so the complex two-dimensional space, you take a projective space of that. So each fiber you take a projectivization. Then each fiber is a CP1 fiber. So this is a S2 bundle over S2. It is twisted, but it's S2 bundle over S2. And this is a Hirzebruch surface. And then let's calculate. So what is this? H star of M is isomorphic to Z. We have V1, V2, V3, V4, 4 facets, right? And quotient by I. I means what? I is a generator where you have intersection of facets is empty. So there are two. I mean, you need to choose the minimal one. So F1 times F3 is 0. F2 times F4 is 0. So V1, V3, and V2, V4. Multiplication. This is I. Okay? And what is J? J is here. You read this way. So V1 plus V3 and V2 plus P V3 plus V4. So you are modding out these two relations. And then from this, V1 is V3. And from here, V2 is PV3 plus V4. So this one is same as Z V3 V4 with V3, V1 is V3 minus, but just a plus minus sign doesn't make much difference. So V3 squared, and then what you have is V4 PV3 V4. So this is the cohomology ring of the Hirzebruch surface. You can completely calculate this cohomology. Okay, I don't have much time. So this is usually what happens when you prepare 10 pages. You usually end up with 7 pages and without doing any. So let me give you one interesting question here. And it's still open and it's still very interesting, very easy to explain. Everybody can understand the problem, okay? So let me give you this open problem here. So the question is, suppose M and N are 2n-dimensional, two quasi-toric manifolds, and their cohomology rings and as graded rings. Okay, then does this imply that M is homeomorphic? This looks very rude, right? Because cohomology is not a very nice invariant to distinguish spaces. But so far, no counterexample to this problem. Okay, so for this, let me narrow down this question to a more reasonable subclasses of manifolds where you can think of. So let me talk about again, this name is also not so fair because this construction first appeared in a paper by Bott and Samuelson. And then Cashon and Ginsberg, or Grossberg, they wrote the paper and they named it as Bott tower. What happened to Samuelson? Probably Bott is more famous. Yeah? But anyway, construction is this. So I'm going to not generalize, but just Bott tower. So you start with point, okay? And then, so this is B0. And this CP1, which is B1. And then it's all fibration. And you see B2, not bad. Let me put it this way. B2 is constructed like a Hirzebruch surface. So you have P of projectivization of any. So this is a complex line bundle over CP1. So this is CP1. So this is the S2 bundle over S2. Okay? And then you keep on doing that. So here you start with the B2. And then consider another S2 bundle. So B3, P of C plus 3 over B2, where this is a complex line bundle over this. And you keep on doing that. Bn. So you have a 2n dimensional manifold. Okay? And the generalized Bott tower is, only difference is that this tower is a CP_n1, and then you have a P of C plus sum of ni's, so n2. So you have sum of n2 line bundles plus constant trivial one. So instead, this is a CP1 bundle over CP1 bundle over CP1 bundle, but generalized one is CPN1 bundle, CPN1 over CPN2 over CPN3, so complex projective space. And then they are all quasi-toric manifolds. Okay, even for the simple case, this one, Bott tower, the question is, B and B prime are two n-stage Bott towers. Bott manifolds or Bott towers, doesn't matter. And suppose H star of B is cohomologically isomorphic to B prime as a graded ring, then B and B prime are homeomorphic. That's a question. And some cases is proved. Okay, there are several cases where this is true. Not only homeomorphism, but we can show that they are diffeomorphic. But generally, it is not proven. Okay, so up to 1, 2, 3, if you have 2 stage, 3 stage, then this is true. And another thing is that in the long chain, all vibrations are trivial, except one place is not trivial. It's rotated, it is twisted. Then it is true. But generally, this is not known. And also, there are some results about generalized Bott tower case, but I don't have much time, so I cannot tell you more about that. But there is another kind of this problem relate with the polytopes. But I have to stop here. Okay.
Are there any questions and comments?